So we've covered till matrix multiplication, and we also looked at um, one way of looking at matrix multiplication, which is essentially composition of linear approximations. We have a couple of more topics on this module, and then we're done. The next important idea that we will look at when it comes to matrices, it's called the rank of a matrix. Okay, another definition that you need to remember, okay? And this is again related to many of the things that we've discussed before. Okay, so the rank of a matrix A is essentially the dimension of the subspace spanned by the columns of A or rows of A. Okay, now when you see these words, right, these things should already remind you of the definitions that we saw in module 1. Okay, we know what is meant by the dimension of a subspace. We know what is a subspace. We know what we mean when we say spanned, a subspace spanned by a set of vectors. Okay, so essentially we're saying if A is a matrix that has some rows A1 to AM, and let's assume A is a n cross n matrix, or it has a bunch of rows A1 till A transpose AM. It's got m rows or n columns. Okay. Now, if you take the columns, right, you can think of the columns as a set of vectors from Rn. There are n such vectors. If I have a set of vectors, I can ask what is the span of these set of vectors. Essentially, what is essentially a new set generated as a linear combination of all the elements in that set. Okay, and we know that forms a vector space or subspace. If I have a subspace, I can ask what is the dimension of the subspace. The dimension of the subspace is essentially the number of vectors you have in any basis for that subspace. Okay? Right. So what we are saying here is if you take a matrix, if you take the columns and then you generate the subspace spanned by these columns, and you ask what is its dimension. Okay? That's the rank of a matrix. Or take the rows, you generate a subspace spanned by these rows, and you ask what is the dimension of that subspace. That will be the rank of the matrix. It turns out that the rank of both the subspace spanned by the columns and subspace spanned by the rows will be exactly equal for any matrix. And that's the rank of a matrix. And that's what I've written here. You will often hear people say column rank or row rank, they will always be equal. Column rank simply means the dimension of the subspace spanned by the columns of A. Row rank means the dimension of the subspace spanned by the rows of it, and they will always be equal, and that is the rank of a matrix. Now, what the rank tells you is essentially the number of independent columns you have in a matrix or the number of independent rows you have in a matrix. That's essentially related to the idea of dimension of the span of the columns or dimension of the span of the rows. And we say that a matrix A is full rank, meaning it has the highest rank possible if the rank of the matrix A, which is an n cross n matrix, is the minimum of n or m. Okay? If the rank can only be, so this is n, this is n, the maximum possible rank for any matrix is the minimum of these two numbers. That means if I have a fat matrix, the rank at the most can be the number of rows of the fat matrix. If I have a column matrix, or not column, if I have a tall matrix, the rank can at the most be the number of columns of a tall matrix. If I have a square matrix, then it can be either the number of rows or the columns. Right? Whenever that happens, that the rank of a matrix equals the minimum of the number of rows or the columns, then you say it's a full rank matrix. And if the rank is less than the minimum of the number of rows or columns, then you say it's a rank deficient matrix. And later on, we will see how to find the rank of a matrix. And maybe next class, we'll discuss that. And then later on in the course, we will also see how to find. We often are not interested in the exact rank, but we are interested in the approximate rank of a matrix, which is practically more useful. So we'll see that as well when we talk about concept called SPD or singular value decomposition. Okay, this is all I want to say for now about rank. For now, just remember this definition, which is essentially the subspace spanned by the columns, dimension of the subspace spanned by the columns or the rows. Okay. Now we come to another important topic called the matrix inverse. We know how to do matrix multiplication, right? And we need to know the rules of when you can multiply two matrices A and B and how to do the multiplication. And we saw 4 different ways of looking at matrix multiplication. And we also know that this sort of an operation essentially means you're composing linear transformations one after the other. Now, it turns out that if you take a matrix and you multiply it by an identity matrix, either post multiply or pre multiply, you will always get the same matrix A. It's just that you have to be careful about the dimension of your I. Okay? If A is an n cross m matrix, then here I should be IM. If A is n cross n, then I here would be IN. So whenever you multiply a matrix by an identity matrix, you get the same matrix back. So it's, in a way, it's equivalent to saying the identity matrix represents 1 for matrices. If what is 1 for real number is the identity matrix for matrices. Okay? And this idea of inverse is essentially inverses that we see in real numbers. If I have a real number x, what is the number y that I can multiply my real number with x with so that I get 1? Similarly, here we are asking, if I have a matrix A, what matrix can I multiply this with? Either post multiply or pre multiply so that I get the identity matrix. And that's essentially the idea of a matrix inverse. Okay. And for now, we will say that matrix inverses exist only for square matrices. We can't talk about an inverse, at least until this point, we can't talk about an inverse for a rectangular matrix. But later on, we'll see that there are inverses possible for rectangular matrices as well. But for now, we'll say whenever you have a square matrix A, we say a matrix B is an inverse for the matrix A if AB or PA is equal to I. And because I said it's a square matrix, let's say it's n cross n, and B is also an n cross n matrix, which produces IN. And this B, so if a matrix B satisfies this, then we say B is the matrix inverse of A. And we usually represent that by A to the power minus 1. Okay. That means if I have a matrix A, and if I know the matrix A inverse, if I post multiply by A inverse, I get IN. If I pre multiply by A inverse, so we said square matrices can have inverses, but not all square matrices will have inverses. Only matrices that are what are called non-singular matrices will have a matrix inverse. And that essentially means non-singular means full rank. It means if you have a square matrix, it's the rank of A. This is the n cross n matrix. If the rank of A is n, then that matrix for sure will have a inverse, and of course that inverse is unique. And later on, I mean, often you'll also hear people say for square matrices, A inverse is both the left and right inverse of A. And we'll see later on that when you have full rank tall or fat matrices, you can only have either a left inverse or a right inverse, not both. But if it's a square full rank matrix, then you have both the left inverse and the right inverse, and both the left inverse and right inverse are unique. One place where, at least analytically, where the inverse of a matrix is useful is when you're trying to solve equations like this, where x is an unknown, a is known, b is known. If you want to solve for x, you might often want to write it like this. Provided a is square and it's full rank, then you can find out the solution for x exists. In practice, of course, you never do this. There are other more efficient ways of doing this. But one use of the inverse, these analytically, is this. We'll look at a couple of properties, important properties. If you have a product of two square matrices, and let's assume both the square matrices are full rank matrices. And if you multiply two square full rank matrices, it turns out the matrix that you get will also be full rank. That means it has an inverse. You can ask, what is the inverse of the product of two full rank matrices? It turns out that the inverse is essentially the inverse of the individual matrices, but in the reverse order. Just like what we saw in the case of transpose, right? AB transpose was B transpose similarly for inverse. And the inverse of an inverse is the original matrix, which again makes sense because if A inverse equals I and A inverse A equals I, if the matrix of interest is A inverse, if you pre-multiply or post-multiply A inverse by A, you get I. That means A must be the inverse of A inverse. And another important property is the inverse of a transpose is the transpose of inverse. Okay, so that's essentially what I wanted to say for most of the module on matrices. We will have a quick look at complex vectors and complex matrices because there are slight differences in some of the definitions that we have when we're talking about complex vectors and matrices. Now we know Rn is essentially a set of all n vectors where the elements are all real numbers. Cn is essentially then is similar. It's simply set of n vectors where all the entries are complex numbers. Okay, and notice that Cn is contained in Rn. Sorry, Rn is contained in Cn. Okay. Now, vector addition and scalar multiplication, we use the same definitions, except that the scalars can now be complex numbers. They don't just have to be real numbers. And the zero vector is the same in Cn. It's a bunch of zeros. And your unit vectors, Ei, are the set of all unit vectors, Ei, form what is called the standard basis for Cn. They were the standard basis for Rn as well. Linear independence, same idea, except now your alpha i's are not real numbers anymore. They can be complex numbers. And the definition is the same. Your alpha i's have to be zero for a set of vectors to be linearly independent if you want to produce a zero vector. If it's any non-zero complex number, then it's still linearly dependent. The inner product is slightly different. In the case of vectors from Rn, this was the definition of the standard inner product. But if x and y are from Cn, the inner product is slightly different. You don't just take the transpose of x, you take x star, okay, which is often also written as x, h. H stands for Hermitian. It's the equivalent of the transpose operation in Rn. So when you do the Hermitian all you're doing is you're doing the transpose. So for example, if I have x1, x2, xn, this is x, and this belongs to Cn. X star would simply be you convert the column into a row. In addition to that, you also take the complex conjugates of each of the individual elements. That's the only difference. If x1 to xn were real numbers, the complex conjugation does nothing because the imaginary part is 0. So this is in fact a more general definition, which applies for both vectors when the elements are real numbers or complex numbers. So that's the only difference for in terms of the inner product. The Euclidean norm remains the same. The square of the 2 norm of a vector x from Cn is essentially x summation multiplied by x, the inner product of standard inner product of x with itself, which gives you this. And you're now essentially not just squaring your individual elements. Individual elements are complex numbers. You take the absolute value, the magnitude of the complex number, and then square that. Orthogonality, the same thing. We say two vectors are orthogonal if their standard inner product in Cn is 0. So that's for vectors. We can similarly define matrices, where the individual elements are complex numbers, not real numbers. And as I said, the transpose operation is essentially a Hermitian operation, where a Hermitian is the transpose of A with and you take the complex conjugation of all the individual elements of A. There are a couple of things that we did not discuss as part of matrices. Okay? We said if you have A, if you take the A transpose operation, you get A transpose. If A is equal to A transpose, right? You do the transpose operation, and the resulting matrix looks like exactly like the original matrix. This can only happen if your matrix is square, because if it's not square, the two matrices cannot be equal, because the tall matrix will become matrix, the fat matrix will become a tall matrix if you do the transpose. So this equating a matrix with its transpose applies only for square matrices, and if they're exactly equal, then A or A transpose is called a symmetric matrix. And we often come across symmetric matrices in many applications. And we will often also come across matrices like this, where A transpose equals minus A. And these are called skew symmetric matrices. The generalization of this applies to complex matrices as well. If A equals A Hermitian, then we say these are called Hermitian matrices, essentially symmetric matrices in the complex domain. Another definition, which again will become clear later on when we discuss the module on orthogonality, is sometimes you have matrices A where the inverse, here I'm talking about A is from Rn cross N. The inverse of A is simply if these are matrices, if these are real matrices, these are called orthogonal matrices. Again, we will come across these often in applications. But if A was, for example, if you had a matrix U, which was a C n cross n matrix, okay, and if U inverse was equal to U Hermitian, then we say these are unitary matrices. Unitary matrices and orthogonal matrices are essentially the same idea, just like Hermitian matrices are the same as symmetric. Right, that's all I wanted to say. And that essentially completes module 2 on matrices. Just a few more definitions for you to remember, but otherwise, most of the material should be fairly straightforward. Okay. So we'll stop here for the module. And if there are any questions that you guys have so far, we can discuss them. Otherwise, we'll do the tutorial for what is left from module 1 and module 2 as well. Okay, I'm assuming there are no questions, so we'll proceed. So we discussed last time. It's good if you have that one sheet with you to be able to do this. Okay, let's look at this problem. These are again problems on the tutorial sheet that is available on the course page. So now we talked about different types of norms. P norm, and P could be a number less than or equal to 1, and non-zero or positive integer. P could be a positive integer. It turns out there is also a zeroth norm that is actually used. Okay? And the definition of the zeroth norm is essentially this. If you have a vector from Rn, x from Rn, the definition of the zeroth norm is essentially this, where this term here is 1 when the ith element is not 0. It's 0 if the ith element is 0. Okay? That means what you're doing on the right hand side is essentially you take the vector and you're counting the number of non-zero values in the vector. That's all. Okay? And if this I is called an indicator function, because you'll come across this in other applications as well. An indicator function takes an arm and it returns 1 if the argument is true. It returns 0 if the argument is false. Now, here the indicator function takes this xi not equal to 0. If it's true, it will return 1. That means if xi is not equal to 0, it will return 1. If xi is 0, it will return 0. That's all. And you're simply adding the output from n indicator function, that will be 1 or 0, which basically tells you the number of zeros and ones that the number of ones that the vector has. Okay. Now the question is this zero norm a valid norm? Essentially, you have to go back and verify there is a few properties that a valid norm for a vector space must satisfy. Does this satisfy all those properties? If it does, then it's a valid norm. If it does not, then it's not a valid norm. And if it does, you have to tell me why it satisfies all of them. If it does not, you tell me which of the properties it does not satisfy. What about the first property? What is the first property? Sorry? It should be a positive, non-negative real number, 0 or more. Is that satisfied by the zeroth norm? Is it always greater than or equal to 0? No. You're saying it'll always be equal to 0? Yes. See, look at the right-hand side. You're adding either zeros or ones, so it can never be negative. So the first one is definitely satisfied. It is always non-negative. So that's okay. What about the second one? What is the second property? Louder. Okay, what is definiteness? X should be the zero vector. Is that true here? So essentially, you have to find out if the zero vector gives you 0, and make sure that no non-zero vector gives you 0. Does the zero vector give me 0 here? Yes. Each of the elements is 0. That means there are n indicator functions. Each of them, what is inside the bracket is not satisfied because xi is equal to 0. That means each of the indicator functions will return 0, and you're adding n zeros, so you get 0. So that's okay. 0 will produce 0. will a non-zero vector produce? Is it possible that a non-zero vector produces 0? Sorry. A what? Then x is 0, right? When x is 0, then this indicator function will give you 0, right? So that is okay. And you can also verify later that if you put any non-zero vector in, you will always get a non-zero value. Okay. So the second one is also satisfied. What is the last one? Or there are two more, I think. Yeah. Yep. What is the third property? Sorry. Yeah. What is that? Explain it to me in plain simple words. If you're able to do it, then that means you've understood it. Understood what that property stands for. Two products. Is it not product? No, it's a scalar multiple. No, if you have a yes. Okay. Or another way to say that if you have a vector, if you have a vector x of a certain length, if I scale the vector by a certain amount, the norm also gets scaled by the same amount, except that you take the modulus of the scaling that you do. Because if you scale by -1, the length of the vector remains the same. So essentially, you're taking the absolute value of the scalar. Is that satisfied here? So if I take a vector, like take a simple vector, ei, or let's say e1 now. E1 is 1, 0, 0, or 0. What is the zeroth norm of E1? Or even, yeah, what's the zeroth norm of this? Simply apply the definition on the right hand side. It's 1. Yes, it's you're simply counting the number of non-zero elements in the vector. It's 1. What about something like this? What would be the zeroth norm of this? 3. That's what. Count the number of non-zero elements. Now, I take E1, I multiply it by 5, and I take what is the zeroth norm of this? What is 5 times E1? It'll be 1, because all you're doing is counting the number of zeros. Is there a problem? No. Is there a problem according to the definition of a valid norm? The homogeneity property. There is, right? Because if my original vector had length 1, if I multiply it by 5 times, then the length of the new vector should be 5 times the original length. But then here you still get 1, and that's where it fails. Okay? It does not satisfy that property. So often, so this is not a valid norm. This is often called the pseudo norm. And in fact, it's quite useful because it essentially measures what's called the sparsity of a vector. How many non-zero elements does it have? Does a vector have? Just out of curiosity, is the triangle inequality satisfied by the zeroth norm? We know homogeneity is not satisfied, so it's not a norm, but out of curiosity. I'll let you think about this. Okay, all right. Okay. Now we look at a problem on linear functions. Okay. Let's say we have a function f, a linear function which takes elements from R3 and returns a real number. Okay? And we know that this we know the output of this. We don't know the function. We don't know the output of the function for any given input, but we only know the output of the function for 3 different inputs. 1, 1, 1 gives me -2. If I input -1, 2, -1, I get 1. And if I input 1, 1, -1, 1, 2, I get 0. Okay. Now the question is, we know that this input produces 0. Can you list other inputs that could produce 0? Or other values of x that could produce f of x equals 0? Given that we know this input-output relationship and that the function is linear. Is the question clear or no? No, if it's not clear, let me tell me. Often the problem is the question is not clear. Okay. I have a function. It takes stuff from R3 and produces elements on the real line. Okay. I can say that I know this function completely if it's possible for me to know if you give me any input from this R3 space, right? If I know what the output will be, then I say I know the function completely. If not, then I don't know the function completely. But here we have this function f, and we know it's linear. I still don't know the function completely because I don't know the input-output relationship. I only know that the input-output relationship is linear. Then somebody comes and tells us, well, if you take this vector 1, 1, 1 and apply the function f, you get -2. Now I know a little bit more. I know the function is linear, and I also know the input-output relationship for one particular input from R3. And then this person also tells us, well, if you input -1, 2, -1, you get 1. Okay? And they give us a third input. If you input -1, 1, 2, you get 0. This is what we know. It's linear, and we know the input-output relationship for these 3 inputs. Now I'm asking you, can you give me other values of x or other points in R3? And if I apply f to those points, I get 0. Given that we know the function is linear and we know the input-output relationship for these 3 inputs. Essentially, you go back to the definition of what a linear function and see a linear function is, and then see if you can figure out from that and the given input, what are all the other possible points from R3 that will give me 0 output. See, one trivial fact about linear functions is if you input 0, it will always give you 0. So that's one possibility. If I input the 0 vector, I'll always get 0. But that's trivial, so that does not count. If the function is linear, it satisfies 2 properties, right? It satisfies superposition. That means it satisfies 2 properties, scaling and additivity. What does scaling mean? In the context of a linear function, what does scaling mean? When I say it satisfies scaling, what does it mean? If I have a vector x that produces f of x, what will c times x produce? Okay. And if this is scaling, addition is if x1 produces f of x1, x2 produces x2, what does x1 plus x2 produce? Well, it's essentially f of given that we know that linear functions satisfy this property, and that you know this for the given function f. can you tell me another input that will produce 0 output? Any combination? Sorry, you'll have to be a little bit more clear. Can you explain what you mean? Okay. Let me call this x1. Okay. This x2, this x3. Okay. -2, 2, 4. Okay. You're saying this will produce 0, is it? Huh? Why? Yes, scale version of x3. If x3 produces 0, then any scale version of x3 will produce c times f of x3, which will also produce 0. That's good. So in fact, any minus alpha, alpha, 2 alpha will give me 0. Great. Is there anything else? Can you use x1 or x2 to produce 0? Can x1, will x1 plus x2 produce 0? x1 plus x2? Exactly. If I do x1 plus 2x2, this will produce f of x1 plus 2 times f of x2. That means it will produce -2 plus 2 times 1. It will produce 0. In fact, any beta times x1 plus 2 times beta times x2 will produce 0. And that's essentially the power of linearity assumption, right? If you know the input to one input, if you know the output to one input, then you know the output for any scaled version of that input. If you know the output to two inputs, then you know the output for any linear combination of those two inputs. Okay. See, in fact, if I ask you what is 5 times x1 plus 4 times x2 and 17 times x3, can you tell me? From this knowledge, from whatever we know about the problem, what will it be? Sorry? So it will be what? -10 plus 4 plus 0, that will be -6. That's advantage. Now, any linear combination of x1, x2, x3, I know what the output will be. That's the power of the linearity assumption. Okay. Now we'll talk about basis, representation of vectors in different bases. Let's say we have a vector x, that's 2, 1. These are vectors from R. Okay. And we've listed 3 set of vectors, A, B, and C. First thing I will ask you is, does the set represented given in the option A, does that form a basis for R2? You'll have to go back to the definition of what is the basis and verify if this set satisfies those properties. Is this a linearly independent set? Yes, it's a linearly independent set. We've also, in fact, we've seen this problem in the previous tutorial session. Here, we verified that this is actually a linearly independent set. It's linearly independent, and this will span R2. That means this is a basis. Now the question is this an orthonormal basis or not? You'll have to go back to the definition of what is an orthonormal basis and verify that those conditions are satisfied. What is the condition for an orthonormal basis? There are two conditions, right? Sorry? No. Okay. Right. Good. Okay. That's the definition. What does it mean in terms of in plain English? When I is equal to j, it should be equal to 1. What does it mean? The inner product of a vector with itself, that is essentially the second norm. So we're saying the second norm should be equal to 1. That means that two norms should be equal to 1, or the length according to the two norm should be of length of value 1. That's the first condition. What about when I is not equal to j? It's 0. What does it mean? No, it means that the vector xi and vector xj are orthogonal, are perpendicular to each other. Now the question is, you simply verify if those two conditions are satisfied here. If you call this x1, this x2, is x1 transpose x1 equal to 1, is x2 transpose x2 equal to 1, and is x1 transpose x2 equals 0. If you're not clear, apply the definition of inner product and verify. The standard inner product and verify. Is the first condition satisfied? Is x1 transpose x1 1? Yeah, that's correct. This is satisfied. What about x2 transpose x2? Yes. What about x1 transpose x2 equals 0? Yeah. Are you sure? It's 0. It is 0. All three are satisfied. That means this is an orthonormal basis vector, or orthonormal basis. Now, I have my vector x. Maybe I should not have used x, but it's fine. I have my vector x. How do I find the representation of a vector x in an orthonormal basis? We said there is something special about orthonormal basis, right? You remember what that special property was? Yes, it's very easy to find out the representation of a vector in an orthonormal basis, right? And how do we find the individual components of the orthonormal basis, of the individual components of the representation of a vector in an orthonormal basis? So here, when we say we are representing x in this basis, right? That means we are saying x can be written as c1 times 1, 0 plus c2 times 0, 1. The question is, how do we find out C1 and C2 for this vector x, where x is? Well, we saw earlier, right? You can find Ci by simply taking your, let me call this y1 and y2. You find out Ci by simply taking x and taking the inner product of, standard inner product of yi with x. Okay? So that means C1 will be y1, the inner y1 transpose multiplied by x. Y1 transpose is 1, 0, row becomes a row vector. My x is 2, 1. This will be 2. C2 will be, again, 0, 1, inner product with 2, 1. That'll give you 1. Means here, the representation of x in this basis is essentially the same, 2, 1. Let's try and do the same thing for the next one. We need to first verify if the second. For now, I'm going to say that both are bases, so you don't have to worry. Both C and B and C are bases for R2. Tell me if B is an orthonormal basis. So you essentially verify the conditions that we talked about. And let's call the first vector y1, second vector y2. The representation of x in this is the same, 2, 1. We now want to find the representation of this vector 2, 1 in this basis, in the B basis. First thing we want to verify if it's an orthonormal basis. Is it an orthonormal basis? Oh, sorry. There is a mistake. Yeah, good one. So this comes in here. Curly bracket is common for both. This 1 by root 2 comes in front of the first vector. So the first vector is 1 by root 2, 1, 1. Second vector is 1 by root 2, 1 minus 1. Now tell me if the set of these two vectors, does it form an orthonormal basis for R2? There are three conditions we need to verify. Is the 2 norm of y1 1? Yes, it'll be 1. Okay. What about the 2 norm of the second vector? y2. This is y1. This is y2. What about the 2 norm of y2? Yeah. What is the question? No. Two norm is easy to calculate, no? For the second vector. Is it 1? Why not? Here. What is the 2 norm? See here. There are two ways to do this. You either first find the 2 norm of this vector without worrying about the 1 by root 2, and then simply multiply it by 1 by root 2 later on. Or you take the 1 by root 2 inside. Then it will be 1 by root 2, 1 by root 2, and then complete. So it will be 1. So the same will apply here. Right? So both of them will have length 1. Now the question is, are they orthogonal to each other? That's the next thing you have to verify. Verify. Check. You sure? So here. Yeah. We're talking about 1 by root 2, 1, 1, transpose 1 minus 1. You can take the scalars outside. Okay? That means you can take the 1 by root 2 outside from the first vector and the 1 by root 2 outside from the second vector. That will be 1 by root 2 into 1 by root 2, which will be simply 1 by 2. Okay? And then you have 1, 1 transpose 1 minus 1, which is nothing but 1 by 2 into 1, 1, 1 minus 1. What is the end product? Product of these two plus product of these two. So in fact, these two are orthogonal vectors. That means this is an orthonormal basis. Now tell me what will be C1, C2. So we want to express X as C1 times. We want to express it C1 times 1 by root 2, 1, 1, plus C2 times 1 by root 2, 1 minus 1. We want to be able to find out C1 and C2. And because they are orthonormal, it's an orthonormal basis, finding out C1 and C2 is quite easy. That means C1 will simply be Y1 transpose X, and C2 will be Y2 transpose X. Y1 transpose will simply be 1 by root 2, 1, 1, multiplied by your original vector 2, 1. That will be 3 by root 2. 1 into 2 plus 1 into 1. No, Y1. So the second one will be 1 by root 2, 1 minus 1, 2, 1. Is it clear? So this will be okay. If you want to verify this, right? Simply substitute 3 by root 2 here and 1 by root 2 here and add the whole thing, and you should get 2, 1. So that's the representation. So in the second basis, the representation will be 3 by root 2 and 1 by root 2. Or another way to write this, you take the 1 by root 2 outside. That's the representation. So for somebody who's working with the B basis, that vector that looked like 2, 1 for somebody working in the A basis, for the B basis, it will be the corresponding representation will be 1 by root 2, 3, 1. The point is the same. Our numbers are different because both of us have different references. That's all. Okay, that's clear. Then let's do the last one. First thing we need to verify if this is an orthonormal basis. Tell me if it's an orthonormal basis. It's not equal to 0. They're not orthogonal, and so that's out. So you only have to test one condition. That means finding out the representation of the original vector x in this basis is not trivial. You can't use an operation like here, like this operation. But what we still want to do, this is still y1 for us. Y1. This is still y2. We still want to be able to find out, represent x as C1 times 2, 1 plus C2 times 1, 1. And x, what is x? X is 2, 1. What values of C1 and C2 could produce this? No, it's not. So because it's not orthogonal, sorry, it's not an orthonormal basis. That means you cannot find out C1 and C2 using this procedure. If the basis was an orthonormal basis, then you can simply do this algebraic procedure to find out the values of C1 and C2. And these are very simple operations. that's the advantage offered by an orthonormal basis. If it's not an orthonormal basis, you cannot do this. But when you say that you want to represent this vector x in this basis, what you're saying is you want to be able to write x as a linear combination of 2, 1 and 1, 1. That means you're saying something like this. So we need to be able to find the values of C1 and C2. Yeah, that's all. It's exactly. If you simply choose C1 as 1 and C2 as 0, then you get what you want. That means that what this means is in this basis, 2, 1 looks like 1, 0. That's all. Okay. If I'd asked you what would 1, 1 look like in this basis, you'd say, well, it looks like 0, 1. That's all. Okay. This problem was easy to solve because I chose one of my basis vectors to look exactly like the vector I want to represent. But if I had asked you, what about -1, 4? How would you represent the vector -1, 4 in this basis? That would require a little bit of work. Okay? You can't use this because it's not an orthonormal basis. But if I asked you for the representation of -4, 1 in these two bases, you would immediately tell me, because you'd simply do this operation, tell me what is C1, C2. If it's not orthonormal, then you have to do a little bit more work, and this simple procedure is not available to us. Okay. All right. I'm going to quickly do the last one. We are almost out of time. You remember that when we spoke about linear functions, we said any linear function, if f is a linear function, we said it can always be written as like this, where w is some constant vector from Rn, and x, of course, is from Rn. No matter what f is, as long as it's linear, we can always find a w that'll where this equality holds for all values of x, and the w will be some constant w. Now, we have a function here. F of x is simply equal to f of xi. And of course, I is fixed here, some fixed I. Let me say for now, this is x4. F of x, if I input my vector, it will simply return the fourth element of that vector. Is this function linear? Sorry? No, here. F takes any vector from Rn and produces R. Okay? So if I, let's say I take a vector like this, 1, 4, -1, 3, and 11. If I apply this function to this, it will return the fourth element in this vector. That means here it will return 3. If I input something else, it will take the fourth element and return that as my output. So for any vector you input, it will simply return the fourth element. If you have a function like that, I'm asking you, is that a linear function? Yes? Yes, you'll find that it is in fact, yeah. Sorry? I didn't hear what you were saying. You'll have to be a little louder. No, so okay, it's simply this. I give you the vector, and the person, there is a box. I send the vector into the box. The person is sitting inside. The person simply takes out the fourth element of the vector and sends it out. That's all that person is doing, or the box is doing. So the question is, does this box represent a linear? Yes, it satisfies both scaling and addition, or it satisfies superposition, because if I input 4 times my vector x, what I will get out is 4 times x4. If I input x1, vector x1, I get the fourth element of vector x1. If I input vector x2, I get the fourth element of vector x2. If I input x1 plus x2, the fourth element of x1 plus x2 is the sum of the fourth element of x1 plus the fourth element of x2. That means I'll get the sum of the fourth element of x1 plus the fourth element of x2. That means it satisfies scaling and addition. That means it satisfies superposition. That means this is in fact linear. Now the question is, okay, it's a linear function. Can you tell me what the corresponding W is? So I'm essentially saying I have this box to which I put my vector I put in the vector and then it gives me some output. I want to replace this box by simply this vector W, such that if I have my vector, I take the inner product of my vector with this W and then I get the output. What will that W be for this function, for this linear function? That's the question. Not 4. So here, what is W? W is simply W1, W2, Wn. And X, of course, is X1, X2, Xn. If you do W transpose X, what do you get? W1, W2, Wn divided by X1, X2, Xn. The inner product is nothing but W1, X1 is W2, X2, W3, X3, W4, X4, Wn, Xn. We want to be able to choose the values of W1 to Wn such that this gives me X4. What should be the values of W is done? No, what do you mean? Yes, exactly. If you simply choose W to be what? E4, then E4 is the representation of this particular linear function. Okay. If I had given you, if I said f of x produces 2 times x1 minus 4 times x7, what would be the W corresponding to this vector? For this, to this linear function. Okay, so somehow E1 should be involved and E7 should be involved, but that's not enough. 2 times E1 minus 4 times E7 is the vector representing this thing. Essentially just that. Okay, that's the idea. Okay, all right. So we stopped here, and then on Monday we will do the tutorial on matrices, and then look at applications of matrices and vector space. All right.